I want you to try something for a second. Take your index finger and, just run it along the edge of your phone.
Or, I mean, even the desk in front of you works.
Right. Yeah, just pay attention to what you are actually feeling.
Yeah.
It seems completely seamless, right? It just feels like, well, touch.
It really does.
Because we are taught from the time we're in kindergarten that humans have exactly 5 senses, and touch is just one of them. We tend to think of it as this single uniform camera covering your entire body, constantly broadcasting this unified physical reality to your brain.
Yeah, it's a very compelling illusion, but the scientific literature tells a completely different story.
Which is exactly what we're digging into for today's deep dive. We've got a stack of sources on the anatomy and physiology of touch, and our mission today is to figure out how the body actually feels.
Right, because in the medical field, we don't even really use the word touch in that singular catch-all way.
Okay, so what's the proper term?
The proper term is somatosensation, or the cutaneous senses. What you casually experience as one unified feeling is actually a bundle of at least 3 functionally distinct submodalities.
And they run in parallel.
Exactly, running completely independent of one another.
Let's unpack that. 3 completely different submodalities happening at the exact same time.
At least 3, yes. You have mechanoreception, which is the system that handles, mechanical pressure, vibration, skin stretch, and texture.
Okay, that's one.
Then, on entirely different wiring, you have thermoception, which is strictly dedicated to sensing warmth and cold in your environment.
Right.
Third, you have nociception, which is your pain pathway. So that's the alarm system detecting actual or potential tissue damage. And modern neuroscience has recently confirmed a 4th closely related channel called proprioception.
Proprioception. I feel like I've heard that. Is that itch?
It is, yeah.
Wow, okay.
For a long time, researchers just assumed an itch was just a very weak, low-level form of pain, like just a mild firing of the pain network. Right, just like a tiny pain signal.
Exactly. But it turns out it has its own dedicated neural pathway, its own specific receptors, and its own routing to the brain. It is entirely its own system.
So right off the bat, that classic 5 senses folk taxonomy we all learned is fundamentally a biological fiction.
It really is.
To really appreciate how incredibly complex this system is, I think we have to look at how long humanity got it entirely wrong. I mean, the idea of touch being a single sense goes all the way back to antiquity.
Right. We can essentially blame Aristotle for this blind spot.
Yeah, in his work De Anima, Aristotle listed touch what he called haphi as one of the 5 senses.
Right.
He treated it as a single, undifferentiated faculty spread evenly across the whole body like a blanket. And because Aristotle cast such a long shadow over human knowledge, that paradigm held for roughly 2,000 years.
It's amazing it lasted that long.
Nobody really questioned it until, the late 19th century? Yeah, that is when the ancient idea finally began to crack. In the 1880s, researchers like Magnus Blix and Alfred Goldscheider started conducting these incredibly tedious but revolutionary experiments.
What were they doing?
They took tiny, fine probes, sometimes just horsehairs or thin bristles, and began mapping patches of human skin, point by microscopic point, applying different temperatures and pressures.
That sounds exhausting.
It was. But what they discovered fundamentally changed biology. They found that skin sensitivity is punctate.
Punctate. Meaning it's not a continuous sheet of sensation, but rather discrete, non-overlapping spots.
Precisely. If you take a millimeter grid on your hand and touch one microscopic spot with a probe, you might feel a sharp sensation of cold.
Okay.
Move that probe just a fraction of a millimeter to the left, and you feel absolutely nothing.
Wait, really? Nothing?
Nothing at all. Move it another fraction, and you feel pressure. Your skin is a mosaic of highly specialized microscopic spots that only care about one specific type of stimulus.
The sources mention a physiologist named Max von Frey, who took this concept and formalized it in the 1890s.
Yes, into what became known as the specificity theory.
Right. He mapped out these individual spots for touch, pressure, warmth, and cold. But he took it a step further, didn't he?
He did.
He looked under a microscope at the tissue of the skin and tried to match each specific functional spot to a specific, unique anatomical structure.
That was his goal, yes.
Okay, hold on. I have to push back here based on my reading. You're painting a picture of this perfectly gridded map where every microscopic function connects to a tidy, specific anatomical structure.
Right.
Biology is rarely that clean. Did von Frey actually prove this anatomically, or was he jumping to conclusions?
That is a phenomenal question. And you were hitting on one of the most famous instructive failures in the history of physiology.
So he was wrong.
Well, he was substantially right in his core claim, but he failed spectacularly in his supporting details.
That's
He correctly proved the functional specificity of the skin, meaning, yes, different spots transmit different qualities to the brain, but his anatomical mapping was largely incorrect.
Can you give an example?
Sure. He found a structure called a Krauss end bulb in the skin and confidently declared it was the receptor for sensing cold.
And let me guess, it wasn't.
Later science proved that was totally false. Cold is sensed by entirely different mechanisms.
So he had the right idea, but pointed to all the wrong parts under the microscope?
Essentially, yes. But despite the anatomical mix-ups, his legacy is foundational. To conduct his experiments, he invented a tool called von Frey hairs.
I saw those in the notes. What are they?
They are graded filaments. Today, we usually use nylon calibrated to bend at very specific known forces. You press them against a patient's skin until the filament bows, which allows you to objectively measure pain and touch thresholds.
Oh, that's clever.
Medical labs and neurologists still use his exact methodology today.
It's fascinating because von Frey was actually building on even older work from the 1830s by a man named Ernst Heinrich Weber.
Yes, Weber.
Weber was measuring something called the two-point discrimination threshold.
A brilliant early experiment. Weber used a tool that looked like a geometer's compass.
Like the ones you use in math class.
Exactly. He would poke a blindfolded person with both points of the compass simultaneously to find the minimum distance at which those two simultaneous pokes are felt as two distinct points, rather than just one big blurry poke.
And the results vary wildly, depending on where you test. Right.
Wildly.
If you do this on someone's back, those 2 points can be a couple of inches apart, and the person will swear you are only poking them with one single point.
Yes.
But if you do it on their fingertips, the points can be just millimeters apart, and they feel both distinctly.
Right. And von Frey's punctate spot theory finally provided the biological explanation for why Weber's findings happened.
It's about density.
Exactly. It all comes down to receptor density. Your back has very few sensors spread far apart. Your fingertips are packed with them.
That perfectly transitions us to the actual hardware. Because if we have these specialized sensors packed into our skin, how do they actually work?
Right. How do they translate the world?
Yeah, how does the physical act of my finger pressing into the wood of this desk literally turn into an electrical signal that my brain can read?
The mechanism is a biophysical process called mechanotransduction, and it is incredibly, well, mechanical.
How so?
When you press your finger into a desk, you are physically deforming the skin, which in turn physically stretches and pulls the membrane of a specialized nerve ending buried in that tissue.
So the physical pressure is literally pulling a biological door open.
That is an incredibly accurate way to visualize it. That stretching literally pries open microscopic ion channels embedded in the nerve cell membrane.
Okay, and then what happened?
As soon as those channels pop open, charged ions rush into the cell, altering its internal electrical charge. This creates an electrical receptor potential.
Like a battery charging up.
Right. If enough ions rush in and that electrical charge hits a specific threshold, it triggers an action potential, a nerve impulse.
Got it.
That impulse then shoots up the long wire of the axon into your spinal cord and straight up to your brain.
So our skin is essentially covered in millions of microscopic mechanical switches.
Exactly.
And the reading breaks down 4 classic mechanoreceptors that do this heavy lifting. They're categorized by 2 main things, right?
Yes. How fast they adapt to pressure and how big their receptive field is.
Let's walk through them, maybe starting with the slow ones.
Let's do it. Slowly adapting means that as long as the physical pressure is applied to the skin, these receptors keep firing electrical signals. They do not get bored and turn off.
Good to know.
First, we have Merkel cell neurite complexes. These sit very close to the surface of the skin and have incredibly small receptive fields.
Okay, small and slow.
Right. Because they are slow in splitting and have such a tight focus, they are essential for encoding fine spatial detail.
So these are the receptors firing when you run your finger over the raised dots of Braille.
Yes.
Or when you feel the sharp edge of a piece of paper.
Exactly. The second slowly adapting type is the Ruffini ending.
Okay, how are they different?
These have a much larger receptive field, and their specialty is responding to skin stretch.
Stretch.
Yeah, as your hand moves and grasps objects, the skin stretches in different directions. Ruffini endings continuously update your brain about the exact position of your fingers and the direction objects might be sliding across your palm.
Okay, so Merkel cells for fine details. Ruffini endings for skin stretch. Both slow and steady. What about the fast ones?
The rapidly adapting receptors operate on a totally different logic. They fire an electrical burst only when a stimulus starts or when it changes.
And then what?
And then they immediately go quiet even if the pressure remains.
That seems counterintuitive.
Mhm.
Why is a receptor that stops firing useful?
Because you don't always need to know an object is sitting there, you need to know when it's moving.
Ah,
The first of these is the Meissner corpuscle. These are small field receptors located just under the skin's surface. They are perfectly tuned to light touch and low-frequency flutter, around 10 to 50 hertz.
so they tell you when things shift.
Right. Meissner corpuscles let you feel the exact moment a light touch begins. More importantly, they alert your brain the microsecond a glass of water is just starting to slip out of your grip.
Oh, wow. So that allows your muscles to subconsciously tighten before it actually falls.
Exactly. It's an instant reflex loop.
That makes total sense. And that brings us to the fourth one, which is honestly the most mind-bending to me, the Pacinian corpuscles.
They are structurally fascinating. Acinian corpuscles are buried deep down in the dermis, and under a microscope, they look like tiny onions with dozens of concentric layers.
Tiny onions, I love that.
They are rapidly adapting, they have huge receptive fields, and they are aggressively tuned to high-frequency vibration, specifically in the 100 to 300 hertz range.
So to put it all together, Merkel cells are like a high-resolution macro lens for reading the fine print of the physical world. Right? Well, Pacinian corpuscles are like highly sensitive seismographs buried deep in the skin for catching high-speed vibrations.
That's a perfect analogy.
And what's wild about Pacinian corpuscles is this phenomenon the sources call distal attribution.
Oh, yes. This is amazing.
Because these deep receptors are so exquisitely good at sensing vibration, and because vibration travels beautifully through rigid objects, you can actually feel the texture of a piece of paper through the tip of a pen.
Exactly.
You are holding the pen, but your brain projects the sensation of the paper's texture outside of your physical body down to the tip of the tool.
It is a marvel of neurological integration. Your brain processes those micro vibrations traveling up the plastic of the pen, through your skin, and into the Pacinian corpuscles so seamlessly that the tool effectively becomes an extension of your sensory self.
It's like you become a cyborg.
Basically, a mechanic can feel the grinding of a damaged gear deep inside an engine block entirely through the metal handle of a wrench.
Before we move on from pressure,
Yeah.
can we clear up a major misconception? A lot of people assume our fingertips are incredibly sensitive because the skin there is thinner, which supposedly puts the nerves closer to the surface to feel the world better.
I hear that all the time, and that is completely backward.
Backward.
The skin on your palms and fingertips, which is called glabrous or hairless, skin is actually much thicker and tougher than the skin on your forearm, your back, or your face.
Makes sense. We use our hands constantly.
Right, it has to be thick to withstand the constant mechanical wear and tear of interacting with the world.
So if it's not thin skin, the real reason your fingertips are so incredibly sensitive goes back to what we discussed with Weber.
Pure receptor density.
Yeah. You can have up to 100 Merkel and Meissner receptors packed into a single square centimeter on your fingertip.
Yeah.
But it's also about brain power, right?
It is entirely about brain power. The concept is called cortical magnification.
Right, the homunculus.
Exactly. There is a famous map of the body located in the brain's somatosensory cortex, first described by the neurosurgeon Wilder Penfield. It's called the cortical homunculus.
And it looks completely bizarre.
It does. If you draw a human body based on how much brain tissue is dedicated to processing sensory input from each part, the result is this grotesque, heavily distorted figure.
Yeah, it has a tiny torso and tiny legs, but absolutely massive hands and gigantic lips.
Right. Your brain dedicates a disproportionate amount of computational real estate to processing the signals from your hands. It isn't about thin skin. It is about sheer processing power.
Okay, so that covers normal pressure and texture. But what happens when the environment gets extreme?
Extreme, like pain.
Yeah. What happens when you touch a freezing block of ice or step on a sharp pin? The mechanisms have to change, right?
They do. Once we enter the realm of temperature and pain, we leave those specialized corpuscles behind and move to something much simpler.
Which is?
Free nerve endings. These are unencapsulated branches of sensory nerves that just sort of reach up into the epidermis.
Let's talk about temperature first. How do free nerve endings know if something is hot or cold?
They rely on specific ion channels embedded in their membranes, primarily from the TRP family. We usually pronounce it TRP.
Trip channels, okay.
And the discovery of how these molecular thermometers work is exactly what won David Julius and Artem Patapushin the Nobel Prize in Physiology or Medicine in 2021.
Oh, this is the part I was so excited to get to.
It's incredible science. David Julius's laboratory managed to clone a specific channel called TRPV1.
And what does TRPV1 do?
This channel acts as a thermal threshold. It springs open and fires an electrical signal when exposed to noxious heat, basically anything over about 43 degrees Celsius.
Okay, so it warns you before you burn yourself.
Yes, but they discovered something else about TRPV1 that completely shocked the scientific community.
Here is where it gets really interesting. They found that this heat receptor also activates in the presence of a specific chemical molecule,
Capsaicin, the active compound that makes chili peppers spicy.
which explains so much. When you eat a jalapeno, spicy is not a flavor profile that your taste buds are decoding.
No, not at all.
The capsaicin molecule is literally binding to the exact same thermoreceptor on your tongue that evolved to warn you about boiling water.
Exactly.
Your brain interprets a hot pepper as physically hot because, from an electrical signaling standpoint, it is the exact same alarm bell.
It is a beautiful demonstration of molecular hacking by plants, and the reverse is equally true.
Oh, right, with cold.
Yeah. Another channel in the same family, TRPM8, responds to cold temperatures. But researchers found it also responds to the chemical menthol.
This is why a mint leaf or peppermint gum tastes physically cold in your mouth.
Yep. The plant chemical is perfectly shaped to force open your cold receptors.
Okay, so we have TRP channels acting as molecular thermometers. But how does pain fit into this architecture? Nociception.
Nociceptors are specialized free nerve endings designed specifically to signal actual or impending tissue damage, and they operate on two distinct speeds, utilizing two totally different types of biological wire.
Two speeds. What's the fast one?
First, you have A-delta fibers. These are thinly myelinated nerves.
Myelin, that's like insulation, right?
Yes, myelin acts exactly like the rubber insulation on a copper wire. It prevents the electrical signal from leaking out, which drastically speeds up conduction.
How fast are we talking?
A-delta fibers fire signals to the brain at roughly 5 to 30 meters per second. They are responsible for delivering first pain, that fast, sharp, incredibly well-localized sensation.
And the second type of wire?
The C fibers. These are completely unmyelinated.
So no insulation.
Right. Without that insulation, their electrical signals travel at a sluggish pace, usually under 2 meters per second.
That's quite a drop in speed.
It is. They deliver second pain, which is the slow, dull, poorly localized, throbbing ache that lingers.
Let's put this into a real-world scenario for you listening at home. Think about the last time you were walking through your living room in the dark and you violently stubbed your toe on the coffee table.
Ouch.
Right. Instantly, bam. There's a sharp, agonizing, precise pain at the exact point of impact.
That is the A-delta fiber working. The mechanical force of the table crushes the tissue. The A-delta nociceptor fires, and that insulated signal races up your leg at 30 meters per second to scream at your brain, "Move the foot!"
But then you have this awful momentary pause. You've pulled your foot back, the sharp pain fades for a millisecond, and you think, oh no, here it comes.
The dread.
Yeah, the dread. And a full second later, this deep, throbbing, dull ache washes over your entire foot, making you want to just sit on the floor.
That pause is the biological travel time of the second wire. The unmyelinated C fibers were triggered by the exact same impact, but because their signal travels so slowly, under 2 meters per second, it literally takes them a second longer to climb up your leg and reach the brain.
It feels like two distinct events, but it's just two different speeds of data delivery on two distinct physical wires.
Exactly.
Just how separate are these pain wires from the pressure receptors we talked about earlier, like the Merkel cells and the Meissner corpuscles?
They're completely independent systems. To illustrate just how separate they are, researchers like Alexander Chesler have extensively studied patients with a very rare genetic condition.
Okay.
These patients have a loss-of-function mutation in a mechanically gated channel called piezo2, which is essential for normal touch.
What happens when it doesn't work?
Because this channel doesn't work, these patients completely lack the ability to feel gentle pressure. Furthermore, they lack proprioception, meaning if they close their eyes, their brain receives no mechanical feedback from their joints.
So they literally do not know where their arms or legs are in space.
Correct.
That sounds like they are entirely cut off from the physical world. But reading about these patients, the shocking part is what happens when you introduce pain.
Yes, exactly. If you take one of these patients who cannot feel a comforting hand on their shoulder and you prick their arm with a sharp pin, They feel the pain perfectly.
That is wild.
It is, because the nociceptors, the pain system, utilize entirely different molecular machinery than the touch system. The wires for normal touch are broken, but the alarm wires are still fully functional.
I'm struggling to visualize how these systems interact then. If the touch wires and the pain wires run on completely separate parallel tracks from the skin up to the brain, do they ever actually cross?
They do. And understanding where and how they cross led to one of the most monumental shifts in modern neuroscience, the gate control theory of pain.
I've heard of this.
It was proposed by Ronald Melzack and Patrick Wall in a landmark 1965 paper. This theory shattered the simplistic idea that pain is just a faithful alarm wire where more tissue damage automatically equals more pain felt by the brain.
So what did Melzack and Wall discover?
They proposed that pain is actively modulated or filtered long before it ever reaches the brain.
Where does that happen?
It happens right in the spinal cord, specifically in an area called the dorsal horn. Think of the dorsal horn as a sorting facility with a gate. When the small pain fibers, the A delta and C fibers we just discussed, fire, they send signals to the spinal cord trying to open the gate to send that pain message up to the brain.
Makes sense.
However, they share this spinal sorting facility with the large, heavily myelinated, fast-conducting touch fibers, the ones coming from your mechanoreceptor.
The pressure ones.
Right. Melzack and Wall discovered that if you activate those large touch fibers, they trigger inhibitory interneurons in the spinal cord.
Meaning what exactly?
In plain terms, heavy traffic on the touch wires forcefully closes the gate on the pain wires, physically blocking the pain signals from ever ascending to the brain.
Wait, so generating a physical text signal literally cancels out a physical pain signal?
Precisely. The mechanical input overrides the nociceptive input at the spinal level.
Is this why we instinctively rub an injury? Think about when you accidentally slam your elbow into a door frame.
Yes, exactly.
Before you even have time to think about it, you grab your elbow and you rub the skin vigorously. So what does this all mean for you? When you bump your elbow and instinctively rub it, you aren't just comforting yourself. You are literally flooding the spinal gate with touch signals to block the pain signals.
That is the gate control theory in action. You aren't just comforting yourself psychologically. By vigorously rubbing the skin, you are intentionally activating the fast mechanoreceptors in your arm. You are flooding the spinal cord with harmless touch signals, which physically closes the gate and blocks the dull, throbbing C-fiber pain from reaching your consciousness.
That is incredible. But if the brain is constantly modulating and interpreting these signals, it seems like the system could be tricked.
It absolutely can be tricked, sometimes with bizarre results. A classic example in sensory research is the thermal grill illusion.
This is the experiment with the alternating strips of metal, right?
Yes. You take a grill made of interlaced metal bars. You heat alternating bars to an innocuously warm temperature, say 40 degrees Celsius, which feels like a pleasant bath.
Okay, not dangerous at all.
Right. And you cool the other bars to an innocuously cool temperature, maybe 20 degrees Celsius. Neither temperature by itself is painful or dangerous.
Right.
But if a person places their hand flat across the grill, touching the warm and cool bars simultaneously, they will immediately recoil in agony, reporting a paradoxical, intensely painful burning sensation.
But how is that possible? There is no extreme heat and no tissue damage to trigger the pain wires.
It is a massive computational error by the brain. You are inputting strong, warm, and strong, cool signals at the exact same moment from the exact same patch of skin.
So the brain just freaks out.
Pretty much. The higher order circuits in the central nervous system receive this data and get completely confused. The brain essentially computes, extreme cold and warmth simultaneously. In nature, that massive, confusing sensory overload only happens during severe freezing tissue damage or scorching heat.
Wow.
So, to be safe, the brain actively constructs a feeling of painful burning to make you move your hand. It proves definitively that pain isn't just a faithful report of reality. It is an experience actively constructed by the brain based on complex, sometimes conflicting, sensory data.
It shatters that myth that pain is just a faithful transmission of tissue damage. This biology is fascinating, but it isn't just academic trivia. Understanding how these precise receptors work has profound, real-world impacts, particularly in medicine.
It changes everything about how we diagnose disease. Take diabetic peripheral neuropathy, a condition where chronically high blood sugar damages peripheral nerves.
How does this help with that?
We know from the anatomy that this disease characteristically destroys the large myelinated fibers first. That means the Merkel cells and Pacinian corpuscles lose function long before the small pain nociceptors do.
Okay, so the touch goes before the pain.
Exactly. Because neurologists understand this specific biological sequence, they don't wait for a patient to complain about numbness. They proactively screen at-risk patients using those exact von Frey filaments and specific tuning forks.
Oh, to test the vibration and pressure.
Right. If the patient can no longer feel the precise bending force of the filament or the 100 hertz vibration of the fork, the doctor knows the nerves are dying well before the patient is in danger of losing their protective pain sensation.
That's brilliant. And we don't just use this knowledge for diagnosis, we exploit this exact biology in consumer technology every day.
We do. In pharmaceuticals, millions of people use topical capsaicin creams for chronic joint pain.
Which goes back to the chili peppers.
Yes. They are literally utilizing the biology of chili peppers and TRPV1 channels. By constantly flooding those thermal pain receptors, the cream eventually depletes the nerve's neurotransmitters, ultimately numbing the area.
Or using a menthol rub on a sore muscle to trigger the TRPM8 channels for a soothing artificial cold sensation. But it goes way beyond medicine. It is built right into the phone in your pocket. When you are typing on a modern touchscreen smartphone and you feel that little haptic click under your thumb,
Yeah.
there is no physical button moving.
It is pure mechanical deception. The engineers who design smartphones specifically calibrate the tiny vibration motors inside the device to pulse at exactly the 100 to 300 hertz frequency.
Because of the Pacinian corpuscle.
Yes. As we discussed, that is the precise frequency range that your deep Pacinian corpuscles are aggressively tuned to detect. The engineers are bypassing your conscious awareness and speaking the exact mechanical language of your deep skin receptors.
Tricking your brain into feeling a crisp, physical button press that doesn't actually exist in the physical world.
It's incredible engineering.
And the stakes are getting even higher with the development of bionic limbs. Engineers are now building modern prosthetics equipped with artificial sensors on the fingertips that measure pressure and vibration. A computer translates those physical forces into electrical pulses and feeds them directly back into the residual nerve endings in the amputee's arm. They are literally translating the digital world back into the biological language of Merkel cells and Pacinian corpuscles, giving amputees a crude but functional sense of touch again.
It is the ultimate synthesis of all the receptor science we have been unpacking today.
So as we wrap up, I want you to look at your hands again. Run your finger along the desk one more time. Everything you feel, the rough texture of the wood, the warmth of your coffee mug, the sharp edge of a piece of paper, none of it is a single, simple video feed.
Not at all.
It is a brilliant, highly segregated illusion constructed by parallel submodalities working in the dark. From the rapid flutter of a Meissner corpuscle catching a slipping object, to the slow, burning ache of an unmyelinated C fiber warning you of an injury, it is a symphony of specialized microscopic hardware.
It really is. And, if we really want to push the boundaries of just how powerful that illusion is, we have to consider phantom limb pain.
Oh, wow. Yeah.
We talked earlier about the cortical homunculus, the distorted map of your physical body rendered in the tissue of your brain. When a person undergoes an amputation, the physical arm and all of its skin receptors are gone. But that neurological map in the brain remains fully intact.
Because the brain tissue itself wasn't damaged.
Exactly. And because the brain demands input, that map can begin to uncontrollably rewire itself. Sensory input from adjacent areas on the map, like the face, might start bleeding over into the territory that used to process the hand.
That sounds terrifying.
It's strange, for sure. A light brush on the cheek might be shockingly perceived as a touch on a missing thumb. And because, as we saw with the thermal grill, the brain actively constructs pain, it can produce vivid, excruciating, burning agony originating from a limb that no longer exists in physical space.
Just generating pain from thin air.
Yeah. If our entire perception of touch, of pain, and even where our physical body ends and a tool begins is just a series of electrical signals mapped onto a distorted homunculus, a map that can hallucinate a burning hand that isn't even there, then how much of your physical reality is actually out there in the world, and how much of it is just an illusion built in the dark theater of the brain?
That is a staggering thought to leave on. Keep questioning your world. Thanks for joining this deep dive.